to talk about my work on generalized disconnection exponents for Brownian loop soups. Okay, so I start. So I first start by giving background on Brownian loop soups, because I think maybe most people here don't know very well this object. And then I will talk about a few results on decomposition of Brownian loop soup clusters, and many parts of them are joined with Lawler and Werner. And then this part is a motivation for the next question, which is the study of multiple points on the boundaries of the clusters in Brownian loop soups. And this is what the main topic of today's talk. And this is done by computing a generalized disconnection exponents. Okay, so let me start with the background. So for those who don't know about Brownian loop, here is a simulation, an instance of Brownian loop in the plane. So it is in fact just a two-dimensional Brownian motion which starts and ends at the same point. And a two-dimensional Brownian motion is just you put two independent one-dimensional Brownian motion on both x and y coordinates, and it can also be obtained as the continuum limit of a simple random walk on the square grid as the mesh size goes to 0. It was observed by Levy back in 1940 that the law of the chase of a planar Brownian motion is conformally invariant. This is because when you think locally, its chase is invariant under rotation and also under scaling. And this local invariance, in fact, it will give you the global conformal invariance of its chase. So here I just zoom in the simulation to show that it is done on the square lattice to approximate the Brownian motion. So today we'll be interested in Brownian loops. So in dimension 1, a Brownian loop is in fact just a Brownian bridge. If you fix a time t, so I guess everyone knows what is a Brownian bridge. In dimension 1, you just take away a linear function so that it starts and ends at 0. And then in dimension 2, you first fix a root point z in the plane and a time length t, and then you just put two independent Brownian bridges on the two coordinates, and then you get a two-dimensional Brownian loop, which is rooted at point z and with time length t. So this is very easy to understand. But then our goal is to have a measure mu on Brownian loops in the whole plane, which has a random time length and no distinguished root. So this measure on Brownian loops was constructed by Lawler and Werner in 2004. So this measure is a measure on parametrized loops. So a parametrized loop is just a continuous curve that starts and ends at the same point. And the starting and ending point is called the root of the loop. Then one can also unroot a loop by forgetting its root. So two loops are considered to be the same if one can be obtained from another by shifting the root, just as what you see in the picture. Then to construct this measure, they first take this PZT is the rooted loop at root Z with time length t. First, they integrate with respect to the time length t to get a rooted loop with random time length. And then they integrate again with respect to the root z, with respect to the Lebesgue measure on the plane. So yeah, in this integral, there's some normalizing factor in front. I will not go to the details because for this present talk, it is not necessary that you remember this detailed formula for the loop measure. But I just want to remark that you see this integral diverges at t equal to 0 and infinity. So this mu in particular, it is an infinite measure and has infinite mass for very small t and very big t. But it has finite mass if you have a bounded t, not too small or big. Okay, and then from this measure mu, you can construct a Brownian loop soup in the plane as a Poisson point process of intensity c times mu, where c is a positive real number, which is called the intensity of the loop soup. So the bigger c is, the more loops there are in the loop soup. And then for any subdomain of the plane, you can also look at mu d to be mu restricted to those loops that are contained in D. And a Brownian loop soup in D with intensity C is just a Poisson point process of intensity C times mu D. Or another way to see it is you first sample a Brownian loop soup in the whole plane, and then you only keep those loops that are completely contained in D, then you get a loop soup in D. It's just a restriction. So here I show a simulation I made of a Brownian loop soup in the unit square and approximated by a random walk loop soup. You just add loops into the unit square. And I want to remark that if D is a bounded domain, then inside a loop soup in D, there are finitely many big loops. When I say big, I mean you take any epsilon and look at loops with time length or diameter bigger than epsilon. And then you get only finitely many of them because the measure is finite on those loops. However, there are infinitely many small loops because you have an infinite mass on those small loops. And also around each given point, there are infinitely many small loops that encircle it. So in particular, the union of all loops in a loop soup is dense. So in this picture, I have taken away all the small loops in the loop soup so that you do not just see a black square in the simulation. You will see that although I've taken away small loops, but this picture still makes sense because it approximates the cluster shapes of the loop soups. So a cluster of loop soup is a connected component in the loop soup. So here, so two loops are said to be in the same cluster if there is a finite chain of loops that connect them to each other. I say two loops are connected to each other if they overlap each other. It's just you take the union and look at the connected components. So it was shown by Sheffield and Werner in 2012 that a loop soup in D with intensity C bigger than 1 has almost surely one single cluster. So all the loops are almost surely connected to each other. However, if C is smaller or equal to 1, then you almost surely have infinitely many clusters. So there is a phase transition for the critical intensity C equal to 1. So here in the sketch, I show the case you have infinitely many clusters. And then you can look at the outer boundaries of the closures of the outermost clusters. So these are the red loops in the picture. And they form a collection of simple loops, which is distributed as a conformal loop ensemble, also called the CLE. So here is just a sketch, so I only draw finitely many clusters, but in reality, since the loop soup is dense in the plane, so you have, so here on the right, I show a real picture of a CLE. So in this picture, the white region are those parts that are encircled by a loop in CLE, and the black region is what is not encircled. And the black region is a fractal set with Lebesgue measure 0. So if you just randomly take a point, it is almost surely encircled by a looping CLE. So a CLE was introduced by Sheffield, and it is a collection of countably many disjoint simple loops. Yeah, if you take any two loops inside the CLE, they're disjoint from each other, although there is really no space between them because you have finite many small loops that tend to any of the loops. Of course, there is also a non-simple version of CLE that I do not discuss in this talk. So in my talk, the CLE just depends on a parameter kappa between 8/3 and 4. And it can be constructed as the outer boundaries of the clusters in a Brownian loop soup of intensity C between 0 and 1. And there is a 1-to-1 correspondence between C in 0, 1 and kappa in 8/3 and 4. And CLE kappa loops locally look like SLE kappa curves, so Schramm-Werner evolution. And the law of CLE kappa is invariant under conformal maps. Okay, so this is all you need to know about the background. So now let me present some of the results on decomposition of Brownian loop subclusters. So here is a result joined with Van den Werner. So we consider here let lambda be a Brownian loop soup with intensity C between 0 and 1. So it is a subcritical region where you have infinitely many clusters. And then let gamma be the collection of all the outer boundaries, gamma j of its outermost loop subclusters. So this gamma is the collection of these red loops. And also for each j, let OJ be the region which is encircled by gamma j. So this is just the notations we use. Now, the result is conditionally on gamma, conditionally on all the red loops. If you look at the Brownian loops that are encircled by different red loops, then they're conditionally independent of each other. And if you take one of these clusters, so here I take gamma 0, the red loop which encircles the origin, for example, and I conformally map the domain encircled by gamma 0 back to the unit disk, then the image of the Brownian loops encircled by gamma 0 under the conformal map, you get a collection of Brownian loops in the unit disk on the right-hand side, okay? And this law, first, it is independent of the law of gamma 0. And then these Brownian loops, they can be decomposed into two conditionally independent parts. The first part is the set of yellow loops that I mark. Those are the Brownian loops in the cluster that do not touch the cluster boundary. Those are the loops that are in the interior and do not touch the red loop. And also then a collection of these blue loops. They are in the cluster and they touch the cluster boundary. So these two sets of loops, they are conditionally independent of each other. So the yellow loops are just distributed as a usual Brownian loop soup with intensity C in OJ. And the blue loops, they have some other law, but it's independent of the yellow loops. Here I show another simulation I made. So I marked in red the boundaries of the clusters, and I mark in blue those Brownian loops that touch the red boundary, and in black those Brownian loops that do not touch the boundary. But maybe my mesh size is not fine enough, but just to show you give you an idea. So in this same work with Werner, we further obtain a result which is specific for the critical intensity C equal to 1. So when C equal to 1, we have a more precise description of the law of these blue loops in the cluster that touch the boundary. We show that the trace of the union of these loops is distributed as the union of a Poisson point process of Brownian excursions in this same domain. So in other words, like on the picture on the left-hand side, we have these blue loops which come from a cluster in a Brownian loop soup. And then on the right-hand side, we take the same domain and we just sample a Poisson point process of Brownian excursions. And then we say these two, if you look at the trace, they have exactly the same law. So intuitively, on the left, these blue loops, they like touch the boundary and bounce off the boundary. So in fact, they make excursions from boundary to boundary. Each loop makes a successive sequence of excursions. And on the right, you just directly have a Poisson point process of excursions. And we say that the trace are the same. Then later in 2018, in later work, we showed not only the trace are the same, but when you consider them as a collection of excursions, they're also the same because the law of a point process of Brownian excursions in a domain is determined by the law of its trace. So often some people, when they first see this result, they have some questions because on the left-hand side, you have loops. And on the right-hand side, when I draw in the sketch, you feel like you just have excursions and they do not connect into loops. But in fact, in reality, on the right-hand side, there are infinite many small excursions, like very small, like on the boundary. I cannot, of course, draw them by hand. And on the left-hand side, when a Brownian loop touches the boundary, it makes infinitely many small excursions before making a big one. So it really bounces off very often before really leaving. It is just analogous when you think in dimension 1, a Brownian motion, when it touches 0, it really touches 0 infinitely many times before really taking off to make a big excursion. So here in dimension 2, the Brownian loop, when it touches this boundary, it does the same. It just touches infinite many times. So it makes a lot of small excursions. So this is not a contradiction that it has the same law as a picture on the right-hand side. So this result implies that the excursions induced by the boundary touching loops are somewhat independent in some sense, because a Poisson point process is just intuitively just adding excursions one by one in an independent way into the collection. In some way you can think it if it like that. So it's like the excursions are independent from each other. So this is like somewhat surprising because on the left you would expect these excursions are induced by loops, so they should be correlated to each other. But on the right, actually we tell you it is a set of independent excursions. And we believe that this result is specific to C equal to 1, and it is not true for C between 0 and 1. So a last point that I want to mention, it's not a direct consequence of this result, but I want to hope you keep in mind is that a typical point on the boundary does not belong to any Brownian loop, but it is the limit of a sequence of small Brownian loops. So if I take a typical point on this red boundary, so on the left, for example, it is not visited by any Brownian loop. Of course, you see that there do exist the points on the red boundary that are touched by the blue loops, but most points are not touched. Okay. So after this work, we have a few remaining questions. So the first question is, what more can we say about subcritical intensity for C between 0 and 1? Because for this regime, we do not yet have a description of the blue loops that touch the cluster boundary. And so in a later work, we have some partial results on that. So we show that for all intensities C between 0 and 1, the boundary touching loops satisfy a certain type of restriction property with parameter alpha. And this in particular implies the following results, that you have another phase transition at C equal to 14/15. So on the left, you have for intensity C between 14/15 and 1, the boundary touching loops alone almost surely do not form a single cluster. Of course, they originally come from a single cluster. So the fact is, when you add back in those loops that stay in the interior of the domain, then the union of the two will connect into a single cluster. But for C between 0 and 14/15, the boundary touching loops alone already form a single cluster. So it also intuitively tells us that the greater the intensity is, the fewer loops touch the cluster boundary. So another remaining question after this work is, given the excursions, how do we hook them up into loops? How much randomness is involved? So this question is first, we first want to answer it for the critical intensity C equal to 1, because we know that we can have a picture on the right-hand side that shows that you have a Poisson point process of Brownian excursions. And then you would ask, given the excursions, how do you reconnect them into loops? And is there randomness involved? So in order to answer this question, I would first mention a result by Werner. So he showed that in a critical random walk loop soup, at any double point, one can toss a coin to exchange the trajectories without changing the distribution of the loop soup. So for example, on the left, I have two loops that cross each other and have two double points. Then at these double points, I can toss a coin according to some well-chosen probability law and decide to exchange the trajectory. So I have two different loops on the right. And so Werner showed that if we choose well this random way of exchanging at double points, then you do not change the global distribution of the loop soup. So for our question of connecting boundary to boundary excursions back into loops, it is important to know whether there are double points on the cluster boundaries in critical loop soup. Because if you know there are double points, you will at least know that you can do this random exchange at these double points. And this is a motivation that leads us to look at the question of multiple points on the boundaries of the clusters in Brownian loop soups. But I also want to say that this question is also interesting on its own. So let us first define multiple points of a Brownian loop soup. So a point Z is said to be a simple or double or n-tuple point of a loop soup if it is visited at least once, twice, or n times by all the loops together in this loop soup. And so we want to investigate the existence and eventually measure the size of these sets of points. And we will use a host of dimension to measure the size. So let us first see what basic facts we know about them. So if you just take one given point in the unit disk, then it is almost surely not visited by any loop in the loop soup. This is because one Brownian motion almost surely doesn't visit a given point. So in the loop soup, you have countably many Brownian loops, so they also do not visit a given point. But however, the union of the loops is dense and has Hausdorff dimension 2. This is just because the trace of one Brownian motion has Hausdorff dimension 2. And the set of n tuple points of the loop soup also has dimension 2 for any n. This is because this is also true just for one Brownian motion. So we will not be interested, like in general, for multiple points inside the Brownian loop soup because we already have the answers here. But we will be interested in the existence of multiple points on the boundaries of the clusters for the intensity C between 0 and 1. And if possible, in computing their Hausdorff dimensions. So before I go into the loop soup, I just first show what we already know about one Brownian loop or one Brownian motion. It is the same because locally they look like the same. So here I show a Brownian loop on the left, and on the right, its outer boundary. And Vanderbrod conjectured that the Hausdorff dimension of Brownian frontier is 4 over 3. Brownian frontier is just another name for the outer boundary of its trace. And this was later confirmed by Lawler, Schramm and Werner using SLE techniques. Okay. And then it's also known for Brownian loops that there exist double points on the Brownian frontier, and the dimension was computed by Kiefer and Walters. And also it is known that there do not exist triple points on the Brownian frontier. And these dimensions are related to Brownian disconnection exponents that we will explain later. So our work is, we will also use SLE techniques and introduce a more generalized notion of disconnection exponents, which will be adapted to compute these sets on for the Brownian loop soup. But before I go into any details, I just first also want to see some simple facts that we can first deduce without computation. So first, we know that the Hausdorff dimension of the cluster boundaries in a loop soup of intensity C, because this cluster boundary is CLE, so it is locally SLE, and so its Hausdorff dimension is known. It's 1 plus kappa over 8. And it is greater than the Hausdorff dimension of one Brownian frontier. So this tells you that a typical point on the boundary of a cluster does not belong to any loop because the Hausdorff dimension is bigger than the frontier of the Brownian loops. But it is a limit of an infinite sequence of loops. But we also know that there do exist points on the cluster boundaries that belong to at least one loop because the decomposition results that I mentioned earlier, you do have these blue loops that touch the cluster boundaries. Okay, so this is a difference from just the Brownian motion case, because if you look at the outer boundary of a Brownian motion, then every point on this outer boundary is actually visited by this Brownian motion. But now we look at the Brownian loop soup case, and we know that every point on the outer boundary of a cluster, most of these points are not visited by any of the Brownian loops. But we do know that there do exist simple points that are at least visited once. But then if I ask a question, are there double points on the boundaries of clusters in a Brownian loop soup with intensity C between 0 and 1? Actually, we don't know the answer of the question very easily because intuitively, one Brownian loop represents the limit of a Brownian loop with intensity C tending to 0. this is just a heuristic argument. So we would tend to guess that there do exist double points if C is very small, because you are very close to just one Brownian loop. But however, even though that we know that Brownian motions have double points on their boundaries, this does not imply the existence of double points on the loop subcluster boundaries, even for arbitrary small intensity C. So there is actually no way of directly deducing, answering this question of whether there exist double points on boundaries of clusters in a loop soup. Therefore, in order to answer this question, and it seems to us that the only available way is to compute the dimension explicitly. So this is what we will do using generalized disconnection exponents. So let me first mention okay, here. So in this section, all my results come from this paper, Generalized Disconnection Exponents, which will appear in PTRF. So in this paper, we introduce a generalized disconnection exponent, which is an extension of the Brownian disconnection exponent. The latter was conjectured by Duplantier and Kwon in 1988 and confirmed by Lawler and Werner in 2001. And we will compute this generalized disconnection exponent, which will allow us to predict the dimension of multiple points on the cluster boundaries of Brownian loop soups. And in the contrary to the Brownian case, there was no conjecture before on those dimensions by physicists or mathematicians. And so in this paper, which is already written, we just only compute the exponents, but we have this work in progress that we will rigorously establish the dimensions using the exponents. The relation between the dimension and the exponents is just a usual one that I will explain. So for this stage, I just say predict because I only have the exponents, but in a later work, we will compute the dimensions using the exponents. And also, as an important tool in this paper to compute this exponent, we introduce a new family of SLE that we call radial hypergeometric SLE. And this is a natural but substantial extension of the family of radial SLE kappa rows. Okay, so let me just first recall what Brownian disconnection exponents are. So here, first you consider n independent Brownian motions started at n uniformly chosen points on the unit circle. And then you stop them upon reaching a circle of radius r, where r is bigger than 1. Okay, so here I draw just n equal to 2. And let P and R be the probability that the union of the n stopped Brownian motions does not disconnect 0 from infinity. And by scale invariance and the Markov property of Brownian motions, P and RS is smaller than P and R times P and S. And then you take a log of these probabilities, then by subadditivity, you will get a limit of this exponent eta n defined as written in the slide. And this eta n is called the Brownian disconnection exponent. And the value of eta n, as I said, was conjectured earlier, but okay. And then later eta was also further extended to non-integer arguments by Lawler and Werner in 1999, leading to a continuous one-parameter family eta beta. And then later they also computed the value of eta beta. This determination relies on SLE and restriction property of the Brownian motion. And using this value of eta, one can compute the dimension of the Brownian frontier. It is just 2 minus eta 2. So a point is on the Brownian frontier if you have a Brownian motion that visits it and leaves, and they do not disconnect this point from infinity. So in some sense, you have two arms of Brownian motions that go to this point and do not disconnect it from infinity. So that's where comes in the eta 2. And 2 is just a dimension of the plane, okay? And then the dimension of double points on the Brownian frontier is 2 minus eta 4, because if a point on the Brownian frontier is visited twice by a Brownian motion, then it has to come, leave, come again, and leave again. So it's 4 arms of Brownian motion. And also there do not exist triple points on the Brownian frontier because eta 6 is bigger than 2. Okay. So the usual relation between dimension and exponent is just 2 minus. And so, so we will generalize the definition of disconnection exponents for Brownian loop soups. So here, let me give a first definition. So just like before, we consider n independent Brownian motions started at n uniformly chosen points on the unit circle and stopped upon reaching circle of radius r. But this time we also add in an independent Brownian loop soup of intensity C in the whole plane. And for r bigger than s, we take lambda rs, the collection of all the loops in lambda which are contained in B0R but not contained in B0S. And then let P, CNRS be the probability that the union of the n-stopped Brownian motion together with all the loops in lambda RS does not disconnect 0 from infinity. And by scale invariance and macro property of the Brownian motions and the Brownian loop soup, this P, CNR S also satisfies a sub-multiplicative relation. And then we can again take log and take a limit, and we get also exponent depending on the intensity C of the loop soup and n of the number of Brownian motions. And this is what we call generalized disconnection exponents. This is just a first one possible definition, and you will see from this definition, you see it is a very natural extension of the Brownian disconnection exponent. But in our actual work, in this paper, we slightly modified this definition because it will be easier for us to make the computation of the exponents, because we need to connect this definition to SLEs in order to compute. So we first move the starting and ending points of these n Brownian motions all to the same point, to origin, to 0 and 1. And then we add up just an independent loop soup in the unit disk. And we take K and be the field union of the Brownian motions together with all the clusters in the Brownian loop soup that it intersects. And this, we feel this union. So we have such a simply connected set Kn in yellow. And then we can let PCNR be the prob. So we look at the conformal radius of Kn seen from the origin, and look at the probability that this conformal radius is very small. So yeah, and then we take the limit. So it is not very clear that this limit exists from the definition, but then later, using SLE techniques, we show that this limit exists. And of course, the equivalence between definition 1 and 2, we will show it in upcoming work in progress. Okay, so okay, I'll skip a few slides because maybe I don't have enough time. This slide just says that this K and yellow part, we can construct it as general restriction measures, and we construct them using radial hypergeometric SLEs. Okay. Also, I skipped this slide, jump to the prediction. So once we compute the exponents, we are able to predict the dimension of multiple points on the boundary of clusters. So we predict that the dimension of simple point is given by this first formula. And I remark that for C equal to 0, we find the dimension of Brownian frontier. And for C between 0 and 1, this dimension is strictly positive and strictly decreasing in C. So it coincides with our earlier intuition that the bigger C is, the less loops you have that touch the boundary. And the dimension double point is given by the second formula. Also for C equal to 0, this is the same as the dimension double points on the Brownian frontier. And for C between 0 and 1, this is strictly positive and strictly decreasing in C. So once we rigorously establish the dimension, this shows there do exist double points on the frontier of clusters for C between 0 and 1. But however, for C equal to 1, the critical intensity, this dimension will be exactly equal to 0. So this will make it more difficult to say whether there exist double points for critical loops of clusters. Also, there are no triple points for any C. Yeah, so that's what I already said. Once we rigorously prove the predictions, we will be able to confirm the existence of double points on the cluster boundaries for C between 0 and 1. And for C equal to 1, maybe we still have some hope. And so my guess right now is there do exist double points for C equal to 1, but countably many. But this just requires more work to determine. So, okay. And now in the end, I will just use 2 slides to talk about the radial hypergeometric SLEs. So this is an important tool in this work, but I did not mention it earlier because I didn't want to go to the technical details of computation, but I just want to show that this family of, also I denote by HSLE, it is a kind of radial SLE, which depend on one additional false point on the boundary. And it depends on kappa and 2 additional parameters mu and nu. And there are 3 different behaviors. So the first one is that it is, the first case is the same as SLE kappa rho. So it contains SLE kappa rho as a subfamily. So SLE kappa rho is a very common and well-known type of SLE. And the second case too, it would almost really go from 1 to the marked point and leaving the origin on its left. And in the third case, very interesting, it will encircle the origin in a counterclockwise way and then hit itself again. So this is a kind of a new behavior that we see in SLEs because it is otherwise a simple curve, but it still goes back and hits itself. So in the end, I also want to take the opportunity to make some clarification about this terminology of hypergeometric SLE. So in this paper, I introduced a family of radial hypergeometric SLE, and this terminology was introduced by me in earlier work in conformal restriction trichordal case. So where I considered a family of chordal hypergeometric SLE. So now we have the radial counterpart of the chordal case. And SLE itself was invented by Schramm in 1999. And later on, many other families were also considered. So in the chordal case, there was a very well-known and common SLE kappa row 1, row 2 processes introduced by Lawler and Werner in 2002. And then later, Duplantier also considered intermediate SLEs, which depend on kappa and one additional parameter row. And then later in 2016, I considered those chordal hypergeometric SLE, which depend on kappa and 3 other parameters, nu, mu, and lambda. This is where this terminology first appeared. Later, this terminology, as well as the notation HSLE, was improperly used in a series of other works, starting from the first work of Hao. And then she, but in fact, the SLEs that she considered are exactly the same as the intermediate SLE by Zhang. Of course, so my family of hypergeometric SLE contains this family, but it is a larger one. But in many talks and archive preprints, Wu claimed that hypergeometric SLEs were introduced by her without mentioning Zhang's work or my work. So for more details, I'll invite you to see this clarification in section 1.4 of my recent work. So yeah, I want to make this clarification because there is a lot of confusion in the community, and some people think that hypergeometric SLE is the same as intermediate SLE, and this is not the case. Okay, so this is all, and thank you for your attention.
Thank you, Wei. Very, very nice, full-on talk. Okay, anyone? That was very nice, very nice. Anyone? Does anybody have any question? Just unmute yourself and speak. Thank you.
So it seems to me that this works relies critically on conformal techniques.
Yes.
And so, for instance, when you talk about this criticality of this Brownian loop clusters, you're looking at Brownian loops on the complex plane.
Yes.
But on the other hand, there are also two other types of simply connected Riemann surfaces. One is the Poincaré disk equipped with the hyperbolic geometry, and the other one is the Riemann sphere equipped with the elliptic geometry. Would you expect different phenomena if you look at Brownian loops on these different types of Riemann surfaces rather than on the complex plane?
This is a very good question. Actually, yeah, I have not thought about this question before, so it is, but I think locally, you probably observe the same picture because at least locally,
be quite different, even locally. For example, when you look at the Poincaré disk, you're actually using the hyperbolic Brownian motion rather than the Euclidean one. So how does this structure depends on the underlying geometry, depends on this Brownian motion?
Yeah. Okay. Yeah. Thank you for the question. I think it's a very nice question, but since I have not, because I was always working in just the usual Euclidean plane, so
okay.
Yeah, I have not thought about it, but it's worth thinking. So, thank you. Sorry.
It's all right. So.
So may I ask a quick question?
Yeah.
She already mentioned main techniques might be related to conformal mappings, whatever. Is it possible as a take-home thing from your talk to get at least a very general idea how these results can be obtained? Because they look the objects look to be very, very complicated. The whole thing is so difficult. How do you obtain results of this kind?
Okay, so in dimension 2 and in the Euclidean plane, the advantage is that we already know many different tools. As what I said, for example, like SLE, CLE, these type of things. And for the loop soups, we know how to couple loop soup with CLE and SLE. And also, for example, there is something that I did not talk about, but was crucially used in our result, in this result of decomposition of Brownian loop soups, was also a coupling with the Gaussian free fields in the Euclidean plane, in the unit disco. And this coupling only works for C equal to 1 criticality. So it's really thanks to all those couplings between these objects that we can make computation. SLE is a very nice tool that you can make computations because once you have the equations, then you, yeah. So maybe in the, for the earlier question, like in other geometry, maybe there will be some additional difficulty if you don't have these tools of SLE and CLE. Yeah. Yeah, as I said, for computing the dimension, it's really thanks to, as I didn't have enough time, so I passed very quickly here. So I have this object, yellow object, and then I can describe the outer boundary of this yellow object by a SLE curve, this radial hypergeometric SLE. And then I can compute how close this origin stays to this outer boundary. Yeah.
So can I ask one more question?
Yeah.
If we move to dimension 3, for instance, is it possible to study entanglements of Brownian loops and look at a similar notion of clusters, for example, in terms of these chains of knotted Brownian loops?
I think you can certainly define such chains, but for me, I think it is very difficult to really study them and describe them, because in dimension 3 we really have very little tools, and you have such a complicated thing with holes, and yeah. But there are results about, if you just want to know the percolation property, like these things are known actually. I can't remember a reference right now, but I think it was known as in terms of percolation, whether they form an infinite cluster. But not entanglement, because entanglement is more complicated than just overlapping.
And I guess that this entire technique of conformal invariance will break down in dimension 3.
Yes, yes, of course. And that's what makes things much more difficult in dimension 3. Like in general, even in percolation and in general, in dimension 3, there's not, yeah. Yeah.
Any more
And I also, sorry, yeah, maybe I did not mention, but there are also a few other open questions. Yeah. So this question is just about double points on the boundary of the clusters, but then once we know there are double points, there are still questions of knowing how to reconnect the excursions into loops. So my guess is there exist double points, and you can do random exchange as double points, but maybe this is not the only randomness involved in reconnecting. So yeah, just.
All right, we're conscious of the time. So any other questions or comments? No? Well, if not, please join me in thanking Wei for a very, very nice talk.
Thank you very much.